Okay, so for question number 2 in experiment 10, we are asked to draw the Lewis structure for boron trifluoride and also its 3D model along with the bond angle of the molecule. So for this one, what you're going to see is that we are going to do the exact same steps that we did for the first example. The first thing that we have to do is determine the total number of valence electrons in the Lewis structure. So again, remember that the group number is equal to the valence electrons. So for boron, we know boron is in group 3 and there are one of them, so we have one boron and it's in group 3, so it has 3 valence electrons. For the fluorines, we know from the chemical formula that there are 3 of them, and fluorine is in the group 7, so each has 7 valence electrons. And when we go through and we add these up, we see that in our Lewis structure we should have a total of 24 valence electrons. So remember, this is going to be one of those final check things to ensure that you've properly drawn your Lewis structure. So that's step 1. Step 2 is to generate your skeletal structure, basically what is bonded to what. And remember that usually, with the exception of hydrogen, the central atom is written first. So in this case, we see that boron is written first, so we know that it's going to be the central atom, and it's going to be surrounded by the fluorines. So that's step 2. Step 3 is to draw a single bond from your central atom, in this case boron, to your terminal atoms, in this case fluorine. So we draw a single bond from the central atom to all of the terminal atoms. Now, once we've done that, we've done step number 3, we need to give our terminal atoms an octet. And when you do this step, remember you have to pay attention to the things that are exceptions to the octet rule. So, if we look at this, we know that fluorine is not an exception, so that we know it needs 8. And we've already drawn 2 around each fluorine, so we know we have to draw 3 more pairs, or 6 more electrons, around each of the fluorines. And again, when you write these, you can draw these lone pairs as 2 sets of dots, or you can also draw a straight line such as this, which indicates 2 dots as well. Either way, just try to be consistent, and if you're unsure as to which method is preferred by your instructor, make sure that you ask. Okay, so we have given all of our fluorines an octet. We see that we've drawn 3 lone pairs, that's 6, plus the 2 in the bonding, that's 8. So each fluorine has 8 electrons around it. Now we have to ask ourselves, out of the total, how many have I drawn? And if you count them up, you see that we've used all 24 of the valence electrons. So this is a good idea to look at it and say, okay, I could be done. I have to check though, does everything have an octet? Well, I know that my fluorines all have an octet. They all have 8. But I need to consider whether or not boron does. And if I look around it, I see that it has 6 valence electrons surrounding it, which you see is not 8. Now, this is when you have to remember also those exceptions. We said that hydrogen was an exception to the octet rule, where it only wanted 2 valence electrons. We said that beryllium, which we did in the first example, was an exception to the octet rule, where it only wanted 4 valence electrons. And the other exception to the octet rule was boron, and it only wanted 6 valence electrons rather than 8. So if we look at boron, we see, oh, it has 6 valence electrons. So what that means is that it has an octet. So everything has an octet in the molecule, and we've used all 24 of our valence electrons. So we know that this is the correct Lewis structure for boron trifluoride. Now, if we go on to draw the 3D model of this molecule, we know that we have to look and focus on the central atom. So if we look at the central atom, the first thing that we have to do is determine the number of regions of electron density around the central atom. That could be lone pairs, that could be bonding pairs. And what we see for this molecule is that there's 3 regions of electron density on the central atom. And remember, we're concerned only with the central atom for these 3D models. So we see that we have 3 regions of electron density, and all 3 of them are bonding pairs, and I'm going to abbreviate bonding pairs with BP. So when we think about our 3D models and the ones that we've learned in lecture, we know that there are 2 possibilities for our geometry for this particular molecule. That's when we have to pay attention to how are the lone pair, or how are the electron density regions on the central atom. In this case, because they're all 3 bonding pairs, we know that the geometry of this molecule is going to be trigonal planar. And planar indicates that the molecule is flat. So with this particular molecule, what you'll see is that we have to draw this flat, and we have to indicate that all of the fluorines are in the same plane. All of the boron-fluorine bonds are in the same plane. So when drawing the 3D model, you look at the central atom, you see and determine how many regions of electron density are on that central atom. Then you look to see what type of electron density is present, and you narrow down the geometry from there. Now how we draw this is because this is a flat molecule, we need to use straight lines. Now, one of the things that you have to remember about 3D molecules is that these are electrons surrounding this central atom. And electrons have the same charge. Therefore, you know that they repel each other or repulse each other. So, in their 3D model, we have to draw the bonds to the fluorines as far away from each other as they can get. And in this instance, the farthest away from each other that they can get is 120 degrees apart. So the bond angle for this molecule is 120 degrees apart. And we have to draw, as best we can, these boron-fluorine bonds 120 degrees apart. And because it's planar, we also have to use straight lines to indicate that they are all flat and in the same plane. So I have to draw my bonds as close as I can get to 120 degrees apart, and I include my terminal atoms. However, I do not have to include the lone pairs on the terminal atoms. I do not have to draw these lone pairs here on the fluorines in the 3D model. I do in the Lewis structure, but not in the 3D model. Now, if there was lone pairs on the central atom, I would have to include those on the 3D model. However, in this case, there is no lone pairs on the boron, therefore, I do not have to include any lone pairs on my 3D model. So what you see is we have our Lewis structure. Based on our Lewis structure, we've generated the appropriate 3D model, and we've also included the bond angle and the geometry of the molecule. And again, remember, because this is planar, we know that the molecule is flat and that these bonds are all in the same plane. Now, one of the last things that we have to look at is molecular polarity. Now, we've already learned about bond polarity, where we have a bond, and if we look, say, for example, at boron bonded to fluorine, we know that there is a difference in electronegativity. So there is a difference in electronegativity, and as a result, what happens is we have a net dipole moment. So a net dipole moment, where, depending upon the electronegativity, the electrons are going to hang out in this bond on one atom more so than the other, because there is a difference in electronegativity. So there's not equal sharing of those 2 electrons in that bond. So because fluorine is more electronegative than boron, we know that the electrons are going to hang out on the fluorine more, because the fluorine attracts them more. So this ends up generating a partial negative charge on the fluorine. Now, on the boron, because those electrons in that bond are not hanging out there, we know that there's going to generate a partial positive charge on the boron. So the difference between between the partial positive and the partial negative here, this is the net dipole moment. So this would be a polar bond. Now, when we look at a molecule to determine polarity, of a molecule, we have to look at it a little bit differently. We can't just look at the bond itself. We have to consider the whole molecule. Now, when a molecule is polar, okay, so we have polar molecules, we're going to see that we have a net dipole moment, just like what we saw with the bond. But rather, we have to consider all of the bonds at the same time. Now, if you have a difficult time conceptualizing this, think of it kind of as a tug-of-war game, where you are the central atom, and holding your right arm is a football player, and holding your left arm is a 2-year-old. If you think about what net dipole moment is in a molecule, you know that when everyone starts to pull your arms, you are going to be pulled to the right-hand side. That is a net dipole moment in the molecule. So what you have to be able to do is look at the 3D molecule and determine, do I have a net dipole moment? Does my molecule get essentially pulled to one side over the other? Now, if we look at boron trifluoride, what we see here is we know that each individual bond is going to look like this, where we have each bond and we have a partial positive on the boron and we have a partial negative on each of the fluorine due to differences in electronegativity. Now, what you have to consider, though, is do they all cancel each other out, or is the molecule pulled to one side or the other? So when the molecule is pulled, meaning you have a net dipole moment, it is polar. When we have a nonpolar molecule, there is no net dipole moment. So basically what that means is that for here, it gets pulled one direction or the other. For nonpolar, it doesn't. Everything cancels itself out. So if we look at this 3D structure here, we see that because all of them are 120 degrees apart, they all pull, but all cancel themselves out. So with this particular molecule, we would not have a net dipole moment, and this would be considered a non-polar molecule, even though it contains polar bonds. So that's why you have to look at a molecule differently. You can't just consider the bonds, because you can have polar bonds in a molecule, as we did here. But even though you have polar bonds, if they all cancel themselves out, meaning you have no net dipole moment, what that means is that you have a non-polar molecule. Now, in looking at this can be a little bit difficult to conceptualize. However, when we move on to further examples, I'll show you some easy tricks in order to determine the polarity of a molecule.